We have come a long way since the invention of plane by Wright brothers. Thanks to the advancement of modern aviation technology, we can now travel by airplanes more conveniently and efficiently than ever before. Prior to the advent of airliners, it took us about 6 days on a boat from Singapore to Shanghai. Fortunately, now we can reach our destination within 6 hours. According to a report by Flight Radar 24, we have a total of more than 60 million flights in the year of 2019. More importantly, aviation industry continues to prosper. There is a 10% increase over 2018 when we look at the number of daily flights. Then, have we ever asked ourselves, what kind of magic takes a metal behemoth which is more than 70 meters long, carries up to 853 passengers, 320,000 liters of fuel, and a total of 560,000 kilograms of weight into the air and powers it to travel at more than 1,000 km per hour for 15,000 km and 43,000 feet? To find out, we need to resort to the power of physics, more specifically, aerodynamics. To answer the question of how airplanes fly, we need to enter the world of aerodynamics, which is the study of how gases interact with moving bodies. When thinking about what takes those heavy objects into the air, we will certainly think of jet engines, where the combustion of fuel and air happens. However, engines are not the most crucial reason for this. Things can fly without engines, as gliders and birds readily illustrate. What really matters for airplanes and shows the ingenuity of mankind are their wings. At extreme high speed, which is approximately 900 km per hour for airliners, the influence of airflow is intuitively significant. Wings utilize this rapid airflow to provide lifting force, thus keep the plane in the air. To conclude, engine's role is to move a plane forward, while wings carry it upward. Now we will take a deeper look at the mechanism of the wings of airplanes. Firstly, let us draw a free body diagram of an airplane. There are mainly four forces imposed on an airplane. Thrust, provided by engines, pushes the airplane forward. Air resistance tends to slow the airplane. Weight's opposing force is lift, which holds an airplane in the air. There is something unique about the wing. The shape of the wing is asymmetrical when looking at its cross-section. This specific shape is known as airfoil, which has a curved top and a nearly flat bottom. This statement is true across the whole history of human aviation. From Wright brothers aircraft to Concorde and A380, this structure is always seen on almost any aircraft. Then, how does this airfoil contribute to flying? There is one misconception regarding how airplanes fly, that is, the lift is created by the pressure difference as air speeds up, its pressure drops. Thus, the faster airflow over the wing exerts less pressure on it than the slower air moving underneath the wing. This will result in an upward push. This phenomenon is known as Bernoulli's principle in the field of fluid dynamics. Unfortunately, the proper explanation of it is common, quick, it sounds logical, yet also introduces misconceptions, uses a nonsensical physical argument, and misleadingly invokes Bernoulli's equation. Imagine two air molecules at the front of the wing and separated. One goes up over the wing, and other goes under the bottom of the wing. There is no valid reason for these two molecules to reach the back of the wing simultaneously. This flaw in the standard explanation of an airfoil goes by the technical name of the equal transit theory. This theory is not capable of addressing some common phenomenon as well. For example, experienced pilots can fly inverted. However, according to the theory, they are undoubtedly not able to do that because the air pressure difference will cause the plane to fly towards the ground. A new idea proposed that an airfoil fly through the sky. The wing deflects air and changes air pressure in its vicinity. The natural inclination of air is to travel in a straight line. However, the curve of the wing acts as an obstacle to stretch the air. As the volume is increased, the pressure is lowered. The lower half of the wing compresses the air in front of it. This is the origin of the pressure difference. As a side note, difference in pressure which is attained from the result of wind tunnel is much bigger than the prediction from the eco-transit theory and Bernoulli's principle.
Now, let me introduce the part of takeoff. For takeoff of an airplane, first, we need to get an understanding about the downwash. The aerofoils of an airplane have a curvature, or camber, to produce a downwash. According to the difference of air density between the top and the bottom of an airplane, downwash causes a pressure difference between the top and the bottom, and makes the lift larger than gravitational force of the airplane, so the airplane can take off. There are three techniques to amplify the downwash and increase lift: high speed, high angle of attack, and the use of flaps. There are 4 stages for takeoff. The first stage is about the change of the configuration. An airplane is lined up on a runway that will give it the best headwind. Flaps, which are the movable surfaces on the trailing edge of the aerofoil near the fuselage, are lowered. This action increases the camber, which amplifies the downwash and helps to create more lift at lower speed. You can see the flaps in the red squares. The next stage is about speeding up. The engines of the airplane are revved up to a certain percentage of full power. This percentage varies among different types of airplanes. Once that value is reached, the brakes are released. The airplane then starts building up speed rapidly, and the throttles are steadily pushed to full power for takeoff. Then it's about to roll out. When the airplane reaches its takeoff speed, the nose of the airplane will begin to lift off the ground. The nose is then raised to a certain angle, which is called the roll-out angle. This changes the angle at which the aerofoils cut into the wind. This once again amplifies the downwash. When the lift is higher than the gravitational force, the airplane will be lifted up. Finally, the airplane is going to take off. Once the airplane is off the ground, the flaps must be retracted. Although they can help the plane to take off from the ground, the flaps will create too much drag when the airplane is flying in the sky. Landing gear, if possible, also needs to be retracted. In most cases, as long as a safe altitude is reached, the airplane will fly away to clear the traffic pattern and let the next plane take off safely.
After we get the idea of how can airplanes take off and remain in the air, we can take a look at how pilots maneuver their airplane. This action is done by controlling different components on the tail and wings of an airplane. We would like to introduce 3 of them: elevators, rudders, and ailerons. On the tail of an aircraft, there are small wings called elevators. This structure has large flaps that are used to change the direction of the airflow. Thus, the pilot can tilt the plane in order to gain or lose altitude. This process is also called pitching. Also on the tail, there is a vertical wing named rudder. This part is crucial for turning the aircraft left or right, which is known more professionally as yawing. The last key component we would like to address is the ailerons, which are horizontal flaps near the end of wings. Appropriate of maneuvering of ailerons are indispensable in both the process of rolling and rotating the plane. So, in conclusion, ailerons causes plane to perform left bank or right bank, and the rudder makes the plane able to do left yaw or right yaw.
Landing is the last part of a flight, as well as the most dangerous one. When the aircraft is ready to land, the pilot will decrease the engine's thrust and activate the flaps and slats to increase the lift and drag. Spoilers are also activated to increase the drag. However, the plane doesn't have to point its head towards the ground as we usually imagine. To explain this, we need to introduce the term angle of attack. Angle of attack is the angle between the wings and the direction of motion of the aircraft. The larger angle of attack is, the more lift and drag increases. Yet angle of attack cannot be indefinitely increased. When the angle of attack is increased to a certain degree, there will be a great number of vortexes on the side of the wing back to air, at which point the lift generated by the entire wing will drop sharply, entering a state where there is little lift, which is called stall. So when the plane needs minimized speed when landing, the pilots usually point the head towards the sky to increase the angle of attack descent. When the aircraft is at a suitable altitude and adjusted to a suitable speed, it will descend at a specific angle. We call this uniform descent rudder slide. In real life, the aircraft generally takes a 3-degree slope down to the slide. When the plane maintains the posture until it reaches the runway, it's time to round out. The pilot will gently pull back the joystick. The nose of the plane will rise from 3 degrees to 5 degrees in order to increase the angle of attack, so that the wing can generate a lift greater than weight. The aircraft obtains an upward acceleration, so the rate of the descent begins to decrease, until reduced to the extent that can gently land on the runway. Rounding out is the most difficult step in the entire landing process. With the hundreds and thousands of practicing, pilots won't be able to finish this little pull subtly. When the aircraft is very close to the ground, the wings and the ground will form air blanketing. Airflow between the ground and the wings will produce a large lift, and this phenomenon is called the wing-in-ground effect. When the pilot feels the obvious wing-in-ground effect, he or she will know that it's time for touchdown. When the plane's rear wheels are grounded, the impact triggers a sensor on the wheel that raises the retarder on the wing. The pilot will also turn on the engine's pushback to assist the aircraft slow down. The front wheels are activated to slowly fall to the ground. They're not as strong as the rear wheels, which means that they cannot withstand strong impact and must be gently put down. But the process cannot be too slow, otherwise the wings do not have enough lift to support the head-up action, and this is a case of a dangerous touchdown. The plane landed on its nose after the front wheels failed to extend. Luckily, in the light of the skilled pilot, no one got injured.
Airplanes have indeed changed the world significantly and continue to be of utmost importance in terms of carrying passengers or cargo items, as well as helping the military in executing its operations successfully. Like all objects, airplanes also have forces acting on it, such as uplift, gravity, thrust, and drag force. If all of these forces are balanced, or if the air molecules continue to push the plane up enough to counter the gravitational force, then the plane stays up in the air at motion. Moreover, the wings and tail play a pivotal role in airplanes since it is engineered with various movable parts that help in maneuvering the plane at high altitudes as well as for takeoff and landing. Thereby, we can contemplate that aeronautics have indeed changed the way we travel and will continue to be a pivotal role for all of us. We hope you all have enjoyed our presentation and thereby have a better understanding with regards to the concept behind how airplanes fly. Thank you very much.